at Oxford. So this is one of the first projects we started with them 8 years ago, and let's see where it goes. So before that, I'm expected to, my university expects me to show this before I share any data of commercial interest. I own shares in Circadian Therapeutics. It's a company that was founded by me with Russell Foster Charity. And part of the funding for the study comes from Circadian Therapeutics and Oxford Science Enterprise, which is very much the capital. So please take everything I say with a grain of salt. So first of all, it's an obvious question. I shouldn't be showing this slide, but I had prepared this. Why target circadian clock? As Shanta said, CDC, which is Center for Disease Prevention, estimates up to a third of a population is experiencing some form of circadian disruption. Not only that, if you look at that, it's interesting. They've been, I don't know how they follow circadian disruption since 1800s. I promise you, this is the data from this blood. But the interesting thing is, if you see, right about here is where the introduction of diatoms. So it seems that this is directly a consequence of us modifying the environment. But on its own is bad enough, but on top of that, if you see some of the other disorders, right? Where diabetes, antidepressant use, and incidence of obesity, they all are starting to peak up post-industrialization. Of course, this does not mean it's merely a correlation. What you should not assume is that I'm saying circadian disruption leads to all these disorders. It's clearly not. There are people who are getting obese but living in today's Shanta's talk and also some of the work that I presented by the drug discovery for metabolic disorders. It seems to influencing circadian rhythm, either with light or with small molecules, seems to have effect. So again, why target the circadian clock? You all are clinicians. When somebody comes with you and tells you they can't sleep, the most likely drug is going to be some kind of hypnotic, right? And we have quite a lot of data, which I'm not showing here, both in cells, in isolated SCNs, and in animal models, that these drugs, such as benzodiazepine, don't have the capability to monitor circadian systems. They're not very efficient, right? Of course, sleep and circadian rhythms communicate. That you might have an effect, but they don't have a direct effect. So there is the need to develop newer therapeutics or environmental interventions to correct circadian disorders, right? So where did we start? So this is where I said I was speaking with, in conversation with Auntie and Russell years ago. My area of interest is targeting signaling pathways. That is my primary interest. And we were discussing, and we said, Russell said, let's look at, let's start making drugs from the point of light pathway. So let's see what the light pathway is. So as you know, the circadian clock is cell autonomous. In the absence of light, okay, without any eyes, the clock will be ticking with its own rhythm, right? Slightly longer than 24 hours in people. So it will be ticking. However, it does have an EBOS, a clock beam time, may create a cryptochrome, which will come back in the next episode. The clock also has a gray element. What it means is when you see light, the retinohypothalamic tract takes this information from the broadstones and melanopsin containing neurons, and it activates cell surface receptor, which leads to increase in calcium and vitamin D, which in turn activates PREP, which point is created. And what happens is, let's say you see light at this point. This will have an acute increase. So the clock is ticking on its own in the absence of Cree, but now you push the Cree button, this one gets amplified. So now concentration of her goes up, and this is what phase shifting at molecular level is, right? You're moving the gene expression before, or you're pushing it after. It's important because everything I will be focusing on later on, will focus on this. So we said, look, this is all signaling system. it's not a metaphysical concept that light is moving clock. It activates a G protein coupled receptor. It increases second messenger, which has been drugged for donkey's years. When you have increased blood pressure, you make angiotensin receptor antagonists, right? It reduces calcium and it prevents the constriction. So we know how to do this. We have phosphodiesterase inhibitor to increase cyclic GMP, right? Viagra, cyclic GMP goes up, and it's a very popular drug. And so therefore we knew there are pathways that we can drug. So we said, let's go and screen molecules that have capability to all the signaling pathways and receptors and see if we can come up with those. This is where it started. So again, let me just go through a bit on target discovery, just because we started at very early stages. You guys can also be familiar with yourself with how a drug discovery program works and where we start. Right? This is the idea. Let's do something. Then if you want to discover a target, you need to develop a drug, you need a target. You need some good validated model. In vitro, ex vivo, in vivo, at all three levels, right? And this is our in vitro model. So what we have is we have a promoter luciferase acid. You kept hearing this. So this is an experiment, real experiment. So as you can see, these are glow in the dark cells. So when pearl level is low, this one goes quiet. When pearl level goes up, this one sort of lights up. Is a promoter luciferase, you give it luciferin, and these go up and down, and this is sped up massively. And what you can do is you can plot this. You can plot intensity of light over time, and you get this nice sine wave. And then what we also have is that we have ex vivo slides. We have genetically altered mice. In this particular mice, what we have is rather than the circadian promoter, the PER2 protein is linked with the luciferase. So we can follow PER2 protein at the SCM. And we have the capability to just dissect out the SCM, the master clock, and culture it. And I think Eric Herzog said he can keep it for 50 days. We never bother more than 2 weeks. But these things can be cultured and followed for a very long time. And finally, we have very, very good animal models. And for drug discovery, this is a phenomenal opportunity, circadian drug discovery, because the gene network is and most disorders do not have this luxury. I cannot emphasize how important this is, right? So for example, if you're developing pain medication, we have tail pinch assay, right? You pinch the tail in the presence of a drug. We all know you can take paracetamol and ibuprofen, get rid of your headache, and if it pinch you, it's still going to hurt. You're going to punch me back, right? So the assays are not very, very good. Same way for psychiatry. If you want to look at depression, we dump a mouse or a rat in a bucket of water and see how much it takes, post-swim test. Which again, it's got some translational value because SSRIs work, but it's our interpretation of what depression should be like in mice, whereas in circadian model systems, it's direct translation, right? So it's a very powerful system, which most, in fact, I would say that haven't come across a model system where it's so translation, so it's very powerful. So here's the drug screening plan. So we said, let's start with 6,000 drugs, and the drug library had every approved drug, Japan, EU, UK, and US. And it also had validated compounds. These are compounds that we had accumulated in the lab over many, many years because of studying other signaling pathways. This included a lot of epigenetic modulators, kinase inhibitors for every kinase. And we had multiple transcription factor modulators, and also natural compounds. We had a handful of natural compounds for which we knew the mode of action, at least in some. And we did a primary phenotypic screening duplicate with 2 different cell lines. So here is U2OS, which is an osteosarcoma, and this one is a B-myelocytosis, which is a hepatocyte. At 10 micromolar, we did it in duplicates. The idea was, if a drug that works on both is going to have cell-independent effects, whereas if a drug works on one and not the other, it will have cell-dependent effects. And the order is to reorder and test the molecule with a complete dose response, and whatever comes out is a validated hit, right? And here's what a screen looks like. So we can culture these cells in 384 cells, well played. And we can ask 384 questions at once. Each well has cells growing in them and a different drug, right? And you can see the date, it's 2016. This was 2019. You can even see when the assays were done. And if I just blow up one quadrant, you can see most of the drugs don't do anything, which is good, which is what we want. If every drug does something, that would be suspicious, right? However, if you see, every once in a while there are drugs that are changing the system. In this case, this particular drug is slowing down the clock. So once we finish this assay for 3 or 4 days of observing what the drug does, then we analyze these parameters. So we look at amplitude, specifically whether drugs can increase the expression of luciferase or beta luciferase. So these are molecular rhythms, right? Gene expression rhythms that we are talking about. So the idea is if BMAL goes up, all the genes controlled by BMAL, the so-called clock control genes, will go up. So very specifically amplitude. And we also look at phase, whether it can move the clock to the time of drug addition, and period, whether it can slow down or speed up the clock. And here's one of the summaries of this drug. So as you can see, majority of the drug don't do anything. However, we have pockets of activity, kinases, hormones, modulators. But we were interested in this group of compound, adenosine-based compound. And this is because we were asking, does adenosine link sleep and circadian system? We got interested in this question. So again, you all are familiar with the two-process model of sleep regulation proposed by Bobelli. This is from a review in '99, and this states the longer you stay awake, the propensity or the sleep need increases as a function of being awake. And this is true of adenosine. Since 70s, people have measured adenosine, and what they have noticed is the concentration of adenosine increases. And in order for the homeostatic drive to reduce, you need to sleep. And when you sleep, the drive goes down, so does adenosine. Adenosine concentration within the brain rapidly falls. And in addition to that, some of you might be cardiovascular surgeons. In order to see if there is any plaque in the arteries, you would give adenosine receptor agonist as an imaging agent, right? Cause vasodilation. One of the other things that happens is oftentimes you make them sit down because they get anesthetized till the drug is metabolized for a short time, right? They fall asleep pretty rapidly. And this is something that is observed widely. If you give adenosine IV, it causes sleep. This massive need for immediate sleep. So all of this made us consider whether adenosine could be one of those molecules that is changing as a function of sleep, is altering circadian system. One other thing that we know, or the field knows, is if you sleep deprive someone, the effect of light on the clock is reduced, or the phase shifting effect is reduced when you sleep deprive someone. Again, all of these are studies done by other people for very, very many years. So this is the reason why we got interested. And of course, we know coffee. So we all drink coffee to fight the effect of sleep, to give that boost. In addition to that, there were studies coming out saying caffeine has the capability to alter circadian clock. So here's a study from Ken Wright and John O'Neill's. Caffeine can alter circadian rhythms in vitro system. It slows down the clock. And not only that, it also phase shifts. And again, here's another study from Yoko Maya's lab reiterating the same thing. And what they found was that SCN's amplitude sort of goes up in the presence of caffeine, right? And here we show that as well. Here we show that when you have the drug, a specific adenosine receptor antagonist, it slows down the clock, but when you wash it, it returns to normal. And after that, we ask the question, what happens if we modulate adenosine itself? And as you can see, even adenosine has a direct effect on the clock. And when we use siRNA to knock out adenosine receptor specifically, that has an effect on the clock. And what this shows is, drugs usually have many, many different targets, but specifically removing adenosine receptors has an effect. And finally, in this case, to the culture media where the cells are, we added an enzyme called adenosine deaminase, which is one of the adenosine metabolizing enzyme. And when you remove adenosine that is being generated by the cell, that's sort of removing adenosine slows down the clock, just as we indicated with adenosine, right? So all of this was looking good. So just so you know, with what the signaling looks like, adenosine is produced by metabolizing ATP, and adenosine has two further routes. So adenosine can be up-phosphorylated to AMP. This is the biggest metabolizing route for adenosine. And there's also an equimolar transporter, meaning adenosine concentration inside and outside are often very similar. Adenosine is transported outside the cell, and adenosine acts on 4 different receptors: A1, A2, A2A, A2B, and A3, which increases cyclic AMP and PKA. Specifically, A2 family is stimulatory, it increases, it activates the system, and A1 and A3 is inhibitory, it suppresses the system, right? It'll be kind of important going forward. A2 is activatory, A1 is inhibitory. So, because of this, what we did was we screened a family of agonists here on its ability to increase cyclic AMP. This is a Newtower cell, by the way. And we also looked at the effect of A1 antagonist, right? And what you see here, adenosine, non-specific adenosine antagonist. As you can see here, adenosine agonist all increases cyclic AMP, whereas adenosine antagonists don't increase cyclic AMP in these cells. And if you look at Krebs activation, which is screen induction, you see the same thing. Adenosine agonist increases cyclic, Krebs activation, whereas adenosine antagonists do not. This was a bit surprising because we were hoping that the antagonists are working by modulating Krebs and cyclic AMP levels, but it was not changing. But we knew it was transcriptional though, because if you look at the gene expression following addition of agonist, which is highlighted in pink, of antagonist, which is highlighted in blue, her levels were changing. But look at the time scale, they're completely different. So we knew they both are activating it with completely different transcriptional pathway. But we had no idea on anything. We knew adenosine receptors are important. We did not know what second messengers they modulate. We do not know what transcription factors they activate. We do not know what transcriptional sequence they bind, right? So it was a black box. So we're sitting and scratching their head. For a while, when Uli Shibler published this fantastic paper in Cells about a technique called spectrum. And what he had done was this. So he has constructed 3,000 transcriptional response elements. So this is CGA, TGG, various transcriptional repeat elements that is repeated 7 times. He's cloned it under the control of a luciferase followed by a synthetic barcode. What this meant was you can culture cells and you can add the drug and harvest the cell at different time points and extract the mRNA and do RNA sequencing. If you do that, you can identify the transcriptional response element that is enriched. So if you do this and if you find a certain sequence is enriched, that would mean something is binding there, right? That's the idea. So anyway, we did this and TopRom told us TGAC, this particular sequence is enriched to a great extent. And when we looked what binds this, it was the transcription factor family AP1, which is a dimer of Fossingium. Now, if you look at that, Fossingium, the literature of Fossingium is very well known in circadian literature again. And if we went one step further, and if we shone light in the mice and we harvested the SCN, we saw lots of gene expression changes. Now, if you ask the question, what genes are being changed as a result, again, the same sequence came, and this particular sequence was preserved highly across the species. So we were fairly convinced this sequence is important. So We identify the sequence, we identify the transcription factor, and I won't go into the detail, but we explored lots of different second messenger signaling that can activate AP1, and we found out it was calcium. And here's the evidence for that. So when you remove AP, the phosphine family of transcription factor, with siRNA, you see the effect of adenosine receptor antagonist disappears, right? So if you remove a transcription factor, the drug which was modulating circadian rhythms are not modulated anymore. And if we knock out ERK, the drug loses potency. So this is the ability of the antagonist to increase the circadian period. But when ERK is knocked out, you see the drug does not have any effect. Don't worry about the point. We had to put that, otherwise we can't predict the. Finally, when we looked at calcium signaling, it did the same thing. The antagonists were raising the levels of calcium in the cell, highlighted in orange, whereas the agonists were not in pink, right? So we figured out that's the final pathway where adenosine antagonists were working with, which is adenosine acts on the receptor, increases calcium, which activates AP1, it binds to the signal and directly feeds into HER2. And early last year we published this paper. If you're interested, you can go and see that. So, knowing up until now all the work has been done in vitro, right? So what is the effect of the drug directly on the SCN? This is where we've taken the SCN out, we've cut a slab, and we are measuring the effect of the drug on the SCN. And first of all, we have to verify adenosine receptors are expressed within the SCN, which they are. There is A1, there is A2A, they're both expressed. A3 and A2B are not expressed within the SCN. So these are the only two receptors that are of relevance. And then if we put two different antagonists, J&J and CGS, you see they do the same thing as they were doing in the cells, which is slow down the clock and increase the period. And again, if you look at the mRNA level, same thing happens. The antagonists increase HER1 and HER2 mRNA. So we've used three different techniques, and all three techniques are saying the same thing. Adenosine antagonist is increasing it's modulating circadian rhythms. Again, all this data are published in these two papers. The first one, the second one just came earlier this year. So you can go and look at all of this if you're interested. So, based on the in vitro and ex vivo data, we made these predictions. A1 and A1A2 antagonists should phase shift circadian rhythms. They should potentiate photic signals, and they should entrain circadian rhythms, right? Because what we're doing is we're amplifying the effect of light on the clock. These were the three predictions. And first, let's see the phase shifting effect of adenosine antagonists, for which what we did here was a complete, or almost complete phase response curve. It's a lot of points, so let me walk you through this. So in the black, so just to take you back, you guys know what phase response curve is, right? So when you shine light at different time of the day, light has differential effects. So in light, you can see at this particular time point, it raised the color, and at this time point, it advances the color, right? So light has a very well characterized phase response curve, which Shanta walked through very clearly. And as you can see in the black, the drug on its own, and the whole mouse is, the mouse is housed in darkness, so it's completely dark. And we shine light at dedicated time points, right? When the mouse is in darkness, if you just give the drug, it doesn't do anything. Again, one other thing is we found if you give IP injection, the mice entrain to IP injection, so the only way to dose the animal has to be oral. So you have to put a gavage and directly deliver it. So in the absence of light, the vehicle does not do anything. 0.2 milligram of the drug has the ability to shift circadian rhythms, very much like light. Light on its own, which is gray, has nice phase shifting effect. And when you give light plus the drug, which is highlighted in yellow, the effect of lights are amplified. So the key take home is this drug on its own can cause phase shifting, and this drug amplifies the effect of the drug. Right? So where will this be useful? Earlier, Kumar was saying that earlier he actually was thinking of going 3 days in advance to a place to entering. This drug might be good in helping you get that fast. And second data is about entrainment. Right? He said this drug will enhance potentiation of 14 signal. So in order to do this, we house the mouse in 12-12 light dark cycle, and where there is the red dot, we gave vehicle in this case and shifted it by 6 hours, right? It's like a eastward flight, and you're looking at jet lag. And under normal circumstance, it takes 1, 2, 3, about 4 or 5 days for the animal to latch on to the new light dark cycle. Now we said if you give the drug at this point, what the effect of the drug is, we asked the question. And as you can see here, as you increase the concentration of the dose, this drug speeds up entrainment. So we move the clock, give the drug. On this particular day, the animal runs as expected. However, on the next day, you can see it sort of wakes up. And if we quantify this, you can see that in the absence of any drug, the animal is responding. The day after. This is 1 day after. This is.
So the drug has to be given just once, right?
Yeah, if you give it after light, the effect becomes smaller. But if you give it before light, the effect is bigger.
But just one time.
Yeah, single time. Single time. It's a single pill. And you can see in the absence of any drug, the animal does advance, but it's smaller, but in the presence of the drug, this is increased. So the final thing is, we were asking, this is the data for entrainment, right? This is where we house the animal in complete darkness. And as mice have circadian rhythm shorter than 24 hours, they wake up earlier each day, slightly. So you have the strip. And for the first 5 days, the animals were not given any intervention. And then on the 5th day, we started dosing the animal, in this case with vehicle. For about 15 days, this is daily dosing, once daily dosing. And finally, for the last 5 days, we removed the drug and let the animal free run. So let's see what the drug does. So this is where the dosing started. The drug was given at sort of that place, and you can see you already seeing very entrainment at very low doses. However, as you increase the dose, the animal is entraining to the drug.
What is the stability of this entrainment? For how many days it remain entrained?
So in this case, the animals were dosed for 15 days. Right?
For how many days the effect remains stable?
It's stable for 15 days at least, we know. We haven't done longer than 15 days. Right? So
Till when the dose is administered, it will be entrained.
that's right now, for 15 days it does, and there is we would predict so, yeah. Yeah, it's daily oral dosing. This one, the other one, the jet lag assay was single dose. This one, because there's no other input, our hypothesis was this drug mimics aspects of light pathway, right? Therefore, if you expose the animal to a light pulse each day for 30 minutes or so, we know the animal will entrain to that even in complete darkness. And our hypothesis was this drug behaves like light, therefore if you leave it here, you should entrain to that, and that is what you see. The interesting thing is, when you stop the drug, the animal starts free running. Right? You see this light drips going on when you stop the drug. And here's the data quantified. You can see this is pre-drug, during drug, and post-drug. Right? And what you see is as you increase the dose, the animal starts moving towards 24 hours. And as you remove the drug, it sort of falls down. So in addition to entrainment, we know adenosine receptor antagonist also has a slow period in Narsingh. So once we saw this, then we asked the question, does adenosine actually communicate sleep state to the clock? remember, that's why we started. We did not start this project to make a drug, to modulate circadian system. We were asking, does adenosine communicate sleep state to the clock? So again, just to reiterate, the longer you are awake, adenosine starts building up in your brain. There is 20 years of research to back this up. There are very many people that have done this. And what we were interested in, does this sleep-mediated increase in adenosine have an effect on the clock? Right? That's the question. So, this result was already known. So what we did was we started measuring adenosine within the brain. So in basal forebrain, when at the end of the active phase, you see adenosine concentration is high, as opposed to end of the sleep phase. And again, just remember these are big changes. The y-axis is in log, right? So these are fairly big changes. And this was already known. Again, other groups have reported this. In basal forebrain, changes in adenosine are sleep rate dependent. But what we show here is by taking SEN punches, we can see this effect even with the SEN, where you have this SEN change. Right? So if this were true, if the statement were to be true, then we know light pulse has effect on the circadian clock in this phase shifting effect. And we see here light pulse does shift it, and this effect is reduced when you sleep deprive the mice and give a light pulse. Right? In this case, light pulse causes a phase advance. When you give sleep deprivation, the light has the effect of light is reduced. However, if you sleep deprive the mouse and give it adenosine receptor antagonist and then give the light, the effect of light is returned. Meaning adenosine definitely has a role to play in this suppressive effect. And we also, when we did this, we were also asked to use a different model system to prove this. So then what we did was we resorted to using a adenosine kinase mutant. Remember, in this mice, adenosine kinase is overexpressed, so the concentration of the adenosine is naturally low. And that should mimic the animal being an antagonist, right? So when we look at this, you can see that at CD22, light has a bigger effect on the clock. And similarly, the animal also has a 24-hour period, slightly longer period as predicted. Remember, when we put adenosine antagonist, the period in the mice went from 23.5 to closer to 24, and that's exactly what we see in a mice which is naturally deficient of adenosine in the brain. Right? So yeah.
Other than sleep wake within, do you see the effect of adenosine on other body?
That is exactly what we are doing now. So what we are doing is, if we use adenosine, so if what he's asking is, if you put mice in a constant jet lag protocol, other people have reported there are metabolic abnormalities, for instance, right? What we are trying to do is, if we put them on a constant jet lag protocol, but at the beginning of every shift, if we give the drug to entrain circadian rhythms, what happens to metabolism, right? Those are the studies. Those are kind of difficult studies, but we are doing it. Hopefully, I have nothing negative or positive to report right now, because they are just literally started. We've not started dosing animals yet for those. So that's weird. Yeah, so very good question. That would be very, very relevant, and there's a big interest to us. How are we doing for time? Maybe okay? Okay. So then we asked the question: why is the clock tracking adenosine? Why on earth does clock care about adenosine? So we hypothesized adenosine is providing information of sleep state to modulate normal rate responses to circadian clock, right? And what I mean by that is, if you are a nocturnal, we know the phase advances are greater at this point than the phase delays, right? It's known. So if you are nocturnal, at this particular point in the light phase, you will be asleep. So when you wake up, there's going to be very little adenosine, right? And as we saw, adenosine is inhibitory. It inhibits, it fights the effect of light. So when the adenosine level is low, in theory, light will have a bigger effect. But as the mind stays awake, the adenosine concentration builds up. Therefore, it starts being inhibitory. Whereas in a diurnal, it's the opposite. Right? We are awake during daytime. Therefore, adenosine will be high at this part, as opposed to end of a sleep phase where adenosine will be low and the phase response curve looks like this. It supports, it's not data, it's just hypothesis, right? We said this phase response curve can partially be explained in terms of adenosine. So now, I'd just like to reiterate this graph, which we saw earlier. So adenosine has two different signaling pathways. One is increasing cyclic AMP and PKA, and the other one is reducing cyclic AMP and PKA. It's slightly more complex than this because adenosine receptor can dimerize with dopamine receptors and lots of other receptors. But for now, let's look at this from these signaling systems. So generally, A1 block or A2A activation is positive for signaling, right? Whereas A2A block or A1 activation is negative signal. I'll put this later on in the figure so you can remember. So then, if a prediction were right, what you would expect is, in a mice where we have a phase shift such as this, if you put a A1 antagonist or a A2A agonist, right, you would amplify the effect. Remember, this is a positive signal. Whereas if you put an A2A antagonist or an A1 agonist, you will compress this rhythm, right? Because it's a negative signal. Again, all of this is in paper. So that is what it is. So A1 activation is negative, A2A activation is positive, A1 block is positive, A2A block is negative, right? And that's exactly what we see. This is it happened exactly as predicted. So you can see, if you compare, the colors are matched to what we predicted, and you can see the results were exactly as we predicted. Therefore, we can do things that adenosine receptors convey circadian timing effect to sleep system to optimize sleep-wake timing. So, clinically viable, this mode of action be useful. So we know what all has happened. So we know what all this drug can do. Then we ask the question, where can we have the most impact with this molecule? And this is where we thought non-24 hour sleep-wake disruption could be good, especially in climate. So early on, what we did was, this is the point where circadian therapeutics was found, and they started taking over the clinical translational work. And what we did first was we collaborated with Blind Veterans UK. So this is an organization who have care homes within the UK. Oftentimes they have blind people both from trauma and other genetic disorders, etc. And they give them lifelong care, both in-house as well as within the institution. And it really helped because Russell, who is one of the founders in Circadian, is also a patron for Blind Veterans UK, right? So he was really helpful in mediating, and what they offered us was their entire facility. And at this time, Suzanne Fatuni, who had trained very well under Shanta, came over to the UK, and she took up as a scientific lead in circadian therapeutics and started spearheading the study with help of a few others. And she started measuring melatonin in non-24 sleep-wake disorders, right? So here is an individual who is partially blind, but clearly he's got pupil responses and light information is working. And if you look at urinary melatonin collected every 4 hours across a 4-week period, you see it's beautifully imitated, right? It's identical. So this is the part where he's going to sleep, and just as he's going to sleep, urinary melatonin concentration increases. And 1 to 4, there's a bit of a wiggle, but usually it's pretty clean straight. But now if you look at this is a person who's totally blind, right? And if you look at his melatonin concentration and urinary AMT across the circadian time point, he's free running, essentially. So what we've done is we've also screened lots of his patients, and we also know what other comorbidities they experience as a function of circadian disruption and metabolic disruption, and we are looking where else this molecule can be used. Can't share the data with you, unfortunately, on that. But it's interesting. But you can see what free running looks like in real life. So why is it bad? Fine, melatonin is free running. So why is it bad? What are the problems that non-24 patient experience? So there is this graph that you can, this picture that might, explain to you. So normally, if you are a healthy individual, your sleep timing might look like this here, right? So at day one, a non-24 patient might start here, where he goes to sleep at 9 p.m., wakes up at 7 p.m. We know, let's assume the circadian period of this individual is 24 and a half hours. What happens if he's free running? That's the sleep window of my level. On day 4, he's already delayed by 2 hours. On day 24, his sleep window is inverted from where he started. And on day 48, he's going to return back. The sleep window is going to return back to where he started. So once every 48 days, his sleep window is optimized to live with normal 24-hour world. And rest of the time, they're always tired, they're cognitively challenged, etc. So this is a really big challenge for this group of patients. Anyway, so progression. So we finished our first in man study, first in human study. The safety study is completed, and with all the preclinical data and safety data, we applied to FDA, and FDA has granted non-24 often this designation for non-24 disorder. So now, then we contacted Shanta, who is the real expert in this, and he has designed a trial specifically to investigate where this drug is going to have the biggest influence, and it's going to, the study is going to have a phase advance arm, it's going to have a phase delay arm, it's going to have 3 doses, placebo, and it's going to have a randomized crossover. And in order to get feedback, what Shanta has also assisted is to help us with building this scientific advisory board. Shanta is sort of the chair of the advisory board, and with sort of input from all of them, we are hopeful that we'll have something by end of next year. So in summary, what we have shown is adenosine concentrations vary as a function of day and night, and then adenosine acts on adenosine receptors, and they hijack the same pathways that light does. And by doing this, adenosine integrates sleep information with the circadian information to give the contextual sleep-wake timing, which serves us into sleep, keeping in mind what the sleep history is. So I'll just stop here, and happy to take any questions. So again, it's just to say this work has been done by very, very many people, and these are the collaborators who are responsible for the 2 publications we have, and the funding is from Circadian Therapeutics, and we are really excited to work with Shanta on this, and thank you very much for leading the scientific advisory board and coming up with the trial. So I'll stop there and happy to take questions. Thanks. We can take a break and come back if you want. No, it's been on, so we just break. Okay, really. System, yeah. So, that's it's a study that shows that you see the light patients reduced when we put in a